Hello, welcome to the class on Advanced Electromagnetic Theory and Antennas. I'm Professor Rakesh Singh Chatrimem. So in this class, we'll discuss about the parabolic reflectors. First, we'll try to find the geometric relations of parabolic reflectors in spherical coordinates. Look at this diagram. This is a parabolic reflector here. The dimension is d here, and this is a coordinate system. You have ax which is coming out of this computer screen, and for the parabolic reflector, any point here, the ray which has gone from the feed antenna and which hits the parabolic reflector and comes back here. So this point here will denote it by P, and this point here at the aperture plane will denote it by Q. So you also have two coordinate system, one X which is coming out from the computer screen. This is the Z axis and this is the Y axis. You have another coordinate system for R dash, theta dash. This is for the source. Usually we denote all the source by dash here. So let us assume that parabolic reflector is a source. In that case, this point here I will have everything with prime coordinates, x dash, y dash, z dash, or I can denote this position by r dash, theta dash also. This theta dash, actually you look at this, if I call this as rm dash, what is this angle? This theta dash make with the z axis at the s of the parabolic reflector is theta m dash, and this distance between the feed antenna and the center of the parabolic reflector will denote it by f. So any rays which has gone from this path from here, it will go from O to the P, then it will go to Q. So this is the aperture plane here. So this distance the ray has gone from the feed antenna to reach the aperture plane is basically this distance plus this distance. This distance is OP, this distance is PQ. So OP is what R dash also denoted by R dash here. PQ will be R dash cos theta. This distance here is r dash cos theta because this angle is also theta dash. So r dash cos theta dash will be this distance here. So OP plus PQ will become r dash plus r dash cos theta dash. And one of the property of the parabolic reflector is that any ray which has gone from this feed antenna after hitting the parabolic reflector comes to this aperture plane, the distance which has been traveled by that ray will be same for all rays you consider here. For example, you consider this central part here, any ray which has gone from this feed antenna hits the parabolic reflector, comes back, that total distance would be equal to this ray here which has gone this distance, then get reflected and comes to this aperture plane. So this distance and this distance should be equal. That means OP plus PQ should be equal to 2f here. This distance is f, so rays which has gone here comes back after reflection will move a distance of 2f. So OP plus PQ is equal to 2f, and it will be always constant. That is the property of parabolic reflector. So at this aperture plane, when you look at the waves, it will become a plane wave. So basically this parabolic reflector converts the spherical wave fronts of the feed antenna to a plane wavefront at the aperture plane. So from this relation you can find r dash is equal to 2f by 1 plus cos theta dash, and you can simplify this, express this as r dash is equal to f secant square theta dash by 2. And this theta dash, you look at it, maximum value will be at the edges here and edges here, and that maximum theta dash will call it as theta m dash, m for maximum. So theta dash is always less than or equal to theta maximum dash. The same relation we have considered in the for the parabolic reflector in the spherical coordinates can be again changed into Cartesian coordinates. So you have the relation r dash plus r dash cos theta dash is equal to 2f. So r dash, what is r dash? R dash is the location P here. This P location here from the origin, how much is the distance? That is r dash. So this is x dash, y dash, z dash. This is 0, 0, 0. That is the origin. So what's the distance between this? OP, that would be simply x dash square plus y dash square plus z dash square root of that. And how much is r dash cos theta dash? R dash cos theta dash is your distance z dash. So r dash cos theta dash is z dash equal to 2f. So you can simplify this, transfer this to the right hand side. becomes 2f minus z dash, then you take square of this, then you get x dash square plus y dash square plus z dash square, square of this 4f square plus z dash square minus 4f z dash. You can simplify it, cancel out the common term here, z dash square and z dash square, you cancel it out. Take out the common 4f here. Finally what you have is x dash square plus y dash square is equal to 4f f minus z dash. This is the same relation you have considered for the spherical coordinates. Now you have the relation for the Cartesian coordinates. In the Cartesian coordinates, x dash square plus y dash square is equal to 4f into f minus z dash. And one more thing is that your x dash square plus y dash square should be less than or equal to d square for 4. What is d? D is the diameter of the reflector. That will be very clear from the next diagram you have here. So here, let's say you consider any point on the parabolic reflector. See, this diagram here is for the parabolic reflector. This is a 3D structure. This parabolic reflector is a 3D structure. You cannot show it properly here, but it's a 3D structure. So if you take the xy plane view of this 3D reflector, you'll see a circle. You'll see a circle, and the circle radius would be d by 2. Diameter will be d. Since this is diameter is d, so radius will be d by 2. This is the xy view of the reflector. So it's a 3D structure. This is the xy view. In that case, this one is the yz view. So if you want to have a xy view, then what you see is origin, from the origin to this edge of the rim of the parabolic reflector, the distance is d by 2, because d is the diameter of this parabolic reflector. If you consider any point here inside this rim here, that would be any arbitrary point x dash y dash 0. Z is 0 here, since z is coming out of this plane here, so z is 0. So the location is x dash y dash. So what is this distance between the origin and the point P, OP? Let's say OP would be square root of x dash square plus y dash square, and that would be having a value from 0 to d by 2. That's why we have this relation x dash square plus y dash square is equal to d square by 4 at the rim of this parabolic reflector. For other cases which are inside this rim of this parabolic reflector, this relation will hold true. X dash square plus y dash square should be less than or equal to d square by 4. And at the rim of the parabolic reflector, this will be x dash square plus y dash square equal to d square by 4. So let us consider the rim of the reflector, parabolic reflector at this rim. In that case, x dash square plus y dash square is equal to d square by 4. And what is the value of z? In that case, the value of z will be minimum for that. For example, value of z will be maximum here when you have z is equal to f. At the edge of this rim, value of the z will be minimum, zm dash. So m for minimum. So note the notation here. M here is theta, m means maximum of theta dash. M here means minimum of z dash. So in that case, we can further use the previous relation. What was the relation? This relation here, you can use it, simplify it at the edges, at this edges here. At this edges here, if you find out this relation x dash square plus y dash square is equal to, it should be at the, on the rim of the parabolic reflector, d square by 4 is equal to 4f into f minus zm dash. So from here you can find out zm dash, and zm dash turns out to be f minus d square by 16f. Once we have this value of zm dash, I am having the value of zm dash at this edges here, so I can find out theta m dash now. Theta m dash will be, tan of theta m dash will be opposite by base, so d by 2 is this length here, and this length is what now? This length here is zm dash, this length is d by 2, so theta m dash will become tan inverse d by 2 zm dash. You can further simplify it. Tan theta m dash will become tan inverse d by 2 square root So basically you have the value of Zm dash here. So you replace Zm dash by this f minus d square by 16f. So theta m dash will become tan inverse d by 2 f minus d square by 16f now. So we are interested in writing theta m dash in terms of f by d. F by d ratio is a very important parameter for the parabolic reflector. F is the distance between the feed antenna and the center of the parabolic reflector, and d is the diameter of the parabolic reflector. So f by d ratio will decide many of the parameters for the parabolic reflector antennas. What we want to do is we want to express this theta m dash, that's the maximum value of the theta dash in terms of f by d, and following the steps which are mentioned here, you can simply find out theta m dash is tan inverse half f by d divided by f by d whole square minus 1 by 16. So you can always find out what is the value of theta dash maximum theta m dash by using this relation. Once you know the value of f by d ratio, usually for the practical parabolic reflector antennas, f by d ratio is taken as 0.5. What I am mentioning is for prime focus parabolic reflector. There are many types of reflector. We'll discuss that one by one in the later part of this lecture. And for that particular case, you can plug in the value f by d is equal to 0.5. Then you can find out theta m dash. Theta m dash turns out to be around 53 degree. Similarly, also you can find f by d in terms of theta m dash. What we have done is we have find out theta m dash in terms of f by d. If I know f by d, I can always find out theta m dash. Let's say I know theta m dash. If I want to find f by d, how do I do it? You can do it easily. See, basically at this edges of the rim of the parabolic reflector antenna, what do you have? Rm dash. This is the distance between the feed antenna and the edge of the rim of the parabolic reflector antenna, and the angle here is theta m dash, maximum value of theta dash. You have the relation Rm dash is equal to R dash is equal to 2f by 1 plus cos theta. That was the first relation we have derived. This relation here, R dash is equal to 2f by 1 plus cos theta dash. This relation is true for any value of theta dash, so it should be also true for theta m dash also. For theta m dash, R dash become Rm dash. So Rm dash is equal to 2f by 1 plus cos theta m dash. Similarly, you can also find out from this relation here, sine of theta m dash will become, sine of theta m dash is opposite is d by 2, and this hypotenuse is Rm dash, so sine of theta m dash is d by 2 Rm. So you can find out Rm from here. Rm dash is simply d by 2 sine theta m dash. So you have Rm dash expression here, Rm dash expression here. You equate those two, you simplify it, then what you are getting is f by d is 1 by 4 cot of theta m dash divided by 2. So if you know what is theta m dash, the maximum value of the theta dash, you can also find out what is the f by d ratio of the parabolic reflector antenna. So what antenna we are considering is called reflector antenna. It usually have two antennas. One is the feed antenna, another is the reflector. You also have other advanced antennas where you have more than one reflector, dual reflector antenna. So most of the time when we consider parabolic reflector antenna, we have a feed antenna and we have a primary reflector. But if you have more advanced kind of antenna, reflector antenna, where you have dual reflector antennas. So those antennas which we consider has a feed antenna at the focal point and one reflector, usually of parabolic shape, those kind of antennas are called single reflector antennas. So in that single reflector antenna, you will have prime focus reflector antenna where you give the feed of the antenna, so feed antenna at the focal point of the parabolic reflector. Offset fed reflector is where your reflector antenna, the feed antenna, is not placed at the focal point of the reflector, it is offset from the focal point. You will see it in the next diagram here, in the next slide. You also have something called Gregorian reflector antennas, where you have dual reflector. There will be a secondary reflector, and this secondary reflector is actually sub-reflector. Secondary sub-reflector is placed at the focal point, and it is fed by a primary feed. And you also have Cassegrain reflectors. This also dual reflector antenna, secondary reflector at the focal point fed by a primary feed. So how does this 4 types of antenna works? It will be clear from the next slide, where we have shown the diagram for each kind of parabolic reflector antenna. So the first one is the primary focus reflector. This is what we are going to study in this class. Will not go into the details of offset fed reflector antenna and Gregorian and Cassegrain antenna. If you are interested, you can always explore. But we'll discuss properly what is this primary focus reflector in this class. In the primary focus reflector, you have a feed antenna at the focal point of this parabolic reflector, and the signals which has grown from here, usually all the parabolic reflectors are analyzed using the rays. So the rays which has gone from this feed antenna is reflected from the reflector antenna, and if you look at it, all the rays are parallel. And that's one of the properties of the parabolic reflector antenna. In the second case, instead of keeping this feed horn antenna at the focal point, it has been offset from the focal point. That is because, let's say you keep this feed horn antenna at this focal point, some of the signals, some of the rays, for example, you consider this ray which goes from this feed horn antenna, it will get reflected, but this ray will be blocked by this feed horn antenna. So that is called blockage. We'll see later on what is the blockage efficiency of the parabolic reflector antenna. When I put a feed horn antenna, it is of finite dimension here. Because of that, any rays which has gone to this path gets reflected back, will be blocked by this feed horn antenna. So there is a cure for that. There is a solution for that. Instead of putting this feed horn antenna at the focal point, you offset it from the focal point, something like this. So any rays which has gone from here will not be blocked. So basically, this rays which has gone from this antenna, feed horn antenna, will get reflected. It will become almost parallel at this aperture plane. So this is called offset fed reflector antenna, where your feed horn is not placed at the focal point, it has been offset from the focal point. You also have advanced version of reflector antenna, where you have dual reflector. So you have one reflector here, this is the called the primary reflector. You also have another reflector here, which is called the secondary reflector. You also have here for the Gregorian and Cassegrain antennas, you have a secondary reflector here. This is the primary reflector, this is the secondary reflector. See, basically your feed antenna is, your feed horn antenna is placed at this location, and it's feeding this secondary reflector, which could be of shape concave shape or convex shape. If it is concave shape, then we call it Gregorian. If it is convex shape, then we call it Cassegrain. So basically, feed horn antenna is feeding this secondary reflector, and rays which has been reflected from the secondary reflector will be again reflected from this primary reflector. With this technique, you can make very large reflector antennas which are used for space communication, satellite communication, planetary exploration, etc. Big antennas which are used for long distance communication. So how does this reflectors work? I have given you an idea. Basically, signals, wavefronts which are coming from this feed antenna at the focal point for the primary focus reflector antenna, it will give you spherical wavefront, but this reflector, after reflecting from this reflector, all those spherical wavefront will be converted into plane wavefronts at the aperture plane. So that's how it works. And in the process, this reflector antenna will concentrate the energy received from this feed antenna into a narrow beam of radiation, and it has a very high gain. You can achieve gains which are greater than 30 dBi. As you already know, 30 dBi is 10 to the power 3. So 10 to the power 3, then you can even have 40 dBi, 10 to the power 4, so on. You can have very high gain antennas by applying this kind of technique where you have a reflector here. And as you know that the basic motivation behind using reflector is to improve the gain of the antenna. So this is how the primary focus reflector works. The idea of this parabolic reflector is that it converts the spherical wavefronts into a plane wavefront. Okay, so let us look at this geometrical figure here and try to find out what is the normal to this parabolic reflector. So the normal to this parabolic reflector at any arbitrary point P is shown by this red line here, red arrow here. This is the normal to this parabolic reflector. And you know what is theta dash, so this angle is theta dash, the r dash make with this z axis theta dash, and again this PQ also has angle theta dash here with the r dash here. So now looking at this diagram, this normal is actually bisecting this theta dash here. In that case, since normal is bisecting theta dash here, look at this diagram here. What is this line here? This line would be negative of r dash. This is r dash. So since we are looking at in this direction, it will become minus r dash here. The vector along this direction and unit vector along this direction will be opposite of the unit vector for r dash. So we'll have minus r dash is the unit vector here. Then this will be the theta dash unit vector here. So normal is actually making an angle theta dash by 2 with the minus r dash unit vector. So this is bisecting this theta dash, so this angle will be theta dash by 2. So in that case, you can easily find the projection of normal along minus r dash unit vector and theta dash unit vector. This will be cos of theta dash by 2. This will be sine of theta dash by 2. So normal unit vector will have two components, one along r dash direction and another along theta dash direction. It is minus cos theta dash by 2 and sine theta dash by 2. Along the r dash direction will be minus cos theta dash by 2. Along the theta dash direction is sine theta dash by 2. This relation would be required later for finding the fields radiated from the reflector antennas. So we are interested in finding the fields which are radiated from the reflector antenna. In the aperture antenna analysis, the first thing we do is find the fields radiated from the aperture and find the gain of the aperture antenna. This is the process, two-step process we have been following for all the aperture antennas. Find the radiated far field radiated fields of the reflector antennas and find the gain of the reflector antenna, aperture antenna. Reflector antenna is also aperture antenna, so we'll try to find the fields radiated in the far field of this reflector antenna and try to find the gain of the reflector antenna. So let us first start with the process of finding the far field radiated fields of a reflector antenna. So here you have, for the primary focus reflector, you have a feed antenna and you have a reflector. Let us first concentrate on the feed antenna. In the feed antenna, let's say the antenna which is used as a feed antenna for the reflector antenna is having far field radiation fields, electric field EF as E naught, function F, vector F, exponential minus j beta r dash by r dash. So this is a standard representation of the far field of the feed antenna. Here you have E naught is a constant, F vector which is dependent on theta dash and phi dash, and this is exponential minus j beta r dash by r dash. This is the usual expression you have for far field of the feed antenna. Usually you use far feed antenna as usually open-ended waveguide or horn antennas are usually used for feeding the reflector antennas. So those kind of antenna will have a far field radiation pattern, electric fields something like this, E naught, F vector, exponential minus j beta r dash by r dash. So now this vector F we can segregate into its two components. One is the theta dash component and this is phi dash component. So F vector can be expressed as F theta dash unit vector, F phi dash unit vector, and F phi theta dash and phi dash will be dependent on theta dash and phi dash again. It's a function of theta dash and phi dash again. So we are interested in finding the fields radiated by the reflector antenna in the far field. It's a three-step process for all aperture antenna. Finding the fields radiated in the far field of the aperture antenna is a three-step process. First step is establish the field in the aperture. Then you take the 2D Fourier transform of the aperture field. Then you find the far field radiated from that aperture antenna by using equation 24.1 and 24.2. We want to establish the first step, that is finding the fields in the aperture. This can be done by using geometric optics, and geometric optics can be used to find the approximate fields of the aperture. And the condition is we should have a large reflector dimension where d by lambda is greater than 100. So you consider dipole antenna. Dipole antenna, we usually have lambda by 2 dipole antenna. So the antenna we are considering now, you can see how much is dimension. This is diameter of this antenna is having dimension 100 times lambda. It should be greater than 100 times lambda. It's a big antenna and it has a very high gain. Sometimes it can have a gain of 1 million also. So for such kind of very large antenna, you can apply geometric optics, GO, to find the approximate fields of the aperture. So the first step, let us try to find the fields in the aperture. That's a usual step for any kind of aperture antenna. Here you can use geometric optics because the reflector dimension is huge. So here on the conducting reflector surface, usually parabolic in shape, on the conductor parabolic reflector, you can apply the laws of reflection. So if you find out reflected waves, basically when you consider plane waves reflection from a media interface, when you have oblique incidence, you consider one is parallel polarization and another is perpendicular polarization. If you have a conductor, you can assume it's a perfect electric conductor. In that case, the reflection coefficient for parallel polarization will become 1. Reflection coefficient for perpendicular polarization will become -1. So from these two conditions, you can find out the relation in the tensile component of the electric field and normal component of the electric field. The tensile component of the electric field will be 0, and tensile component of electric field will compose of incident electric field and reflected electric field. So EI plus, this is the incident electric field, plus E reflected, cross product with the normal vector should be equal to 0. That means tensile component of the electric field is 0 on a metallic surface. And normal component also, N dot EI should be equal to N dot ER. This is from the condition you have here. Reflection coefficient for parallel polarization should be equal to 1, and reflection coefficient for the perpendicular polarization should be equal to -1. So applying these two conditions, you can get these two relation here. So from these two relation, I want to find the field, aperture field. Let's say if I take cross product with the normal unit vector with this first equation, what do I do? N cross EI plus ER cross product with N. Here this is a vector triple product, so you can apply back cap rule. So let's say this is A, B, C, then B will be this, A, B, C. So this is B here, so you write B, then do dot product of A and C. N dot N is 1. This is a unit normal vector, so you do the dot product of a normal unit vector with itself, you get 1. Minus cap, this is C, so N unit vector here. A dot B, so A dot B is N dot EI plus ER. What is N dot EI plus ER? You can get it from here. You can have N dot EI is equal to N dot ER. So I want to replace this ER here. I want to write everything in terms of EI. Then this will also become N dot EI is equal to N dot ER. So I can write, instead of this ER, I will just write EI here also. N dot EI is equal to N dot ER. So I will replace ER by EI here. In that case it becomes 2n dot ei. So here we have only one unknown term here, ER. If I want to find the reflected electric field, it will be simply 2n n dot ei minus ei from this relation here. So this gives the relation of the reflected electric field in terms of the incident electric field, and that is possible from the geometric optics, and that is for the reflected dimension which is very large, greater than diameter of the reflector is greater than 100 lambda. So one point to be noted here is that where is the aperture and where are we considering the aperture? I have already told you before also, I want to tell it again so that you know what's going on. See, basically this is the FIT antenna which is placed at the focal point for the prime focus parabolic reflector antenna, and this is the reflector. This is the parabolic reflector you have here. The aperture we are considering is not the parabolic reflector, so the aperture we are considering is at this location. That's why I have shown aperture here at the focal point. So any rays which has gone from this FIT antenna will get reflected from the parabolic reflector, and it will come here, and this at this Diaz line we are considering aperture. So this right hand side diagram will show it very clearly. We have a parabolic reflector which is a three-dimensional structure. It's a three-dimensional structure. It's a parabolic reflector you have here. So now aperture plane is at this line here, Diaz line here, at z is equal to 0. So what we are doing is basically we are projecting this parabolic reflector at z is equal to 0 plane, and that would be the aperture plane we are considering. So the projected effective aperture would be at the aperture plane. So this will be two-dimensional. This is three-dimensional structure, but this is a two-dimensional structure. And what is the location of this aperture? Aperture is at z is equal to 0. It is simply like a circle, no? So now because of this projection, no, this is actually what we are discussing is some method called aperture distribution method. In this aperture distribution method, I consider the aperture at this plane here at z is equal to 0, and this aperture is a 2D structure, and this is a projection of the 3D parabolic reflector at the z is equal to 0, and that's a technique we are going to use for finding the far field radiated pattern of the reflector antenna. So we are interested in finding the fields at this aperture plane, and what we have here is E reflected is equal to 2n n dot ei minus ei. That is the reflected field at this location. So we have incident field from here, it's coming and it's getting reflected from the parabolic reflector. So what we are considering is the incident electric field here, we are considering reflected electric field here. So this ER is the reflected field at this location at any arbitrary point, let's say P. So how much is the ER here? This is the incident electric field, then how much is the reflected electric field? But what we want to find is the aperture electric field distribution, and that is at z is equal to 0. What is this distance here? This distance here is PQ. So we need to have another phase factor which will take care of this movement of the field from P to Q. That's why we need to have this term here. So let's find out PQ. What is PQ? PQ is R dash cos theta dash. So PQ is R dash cos theta dash. This theta dash, this also theta dash. PQ is R dash cos theta dash. And what is that distance? That distance will be, how much is that? You know that R dash plus R dash cos theta dash is equal to 2f. So R dash plus R dash cos theta dash is equal to 2f. So R dash cos theta dash is equal to PQ is equal to 2f minus R dash. So this movement of the field from this location to this location can be taken care of by adding one phase factor term here, exponential minus j beta. What is this distance? PQ, 2f minus R dash. So this will give me the aperture field. We're interested in finding the aperture field. From there you can find out the 2D Fourier transform of the aperture field. That's the second step. Third step is you use 24(1) 24.1 and 24.2, and find the far fields of the reflector antenna. We have the expression for the aperture antenna, fields on the aperture of the parabolic reflector antenna. And what is EF? EF is the fit antenna field pattern. Once I have EA, I can always find out SA, because they are related. They are in the far field now. So in the far field, your electric field and magnetic field are related, and the ratio of electric field and magnetic field is equal to eta naught. Eta naught is the wave impedance for free space, and it's around 377 ohm. And magnetic field and electric field are perpendicular to the direction of pointing vector, which is along the z direction. So I can write ICA as 1 by eta naught z cross EA. So I can also find out ICA, I can find out EA from this expression once I know the field of the fit antenna, which is EF. This expression is the vector form. I want to find out what is there in the components of this EA and ICA. I'm interested in finding the X component and Y component of EA specifically, so that I can take the 2D Fourier transform. So for that, I have already found out what is the unit normal vector n hat, which was minus r dash hat cosine of theta dash 2 by 2 theta dash hat sine of theta dash by 2. This was n unit vector. We have n unit vector here, n unit vector here we have. So we'll use this relation for the n unit vector. And what is the radiated electric field from the fit antenna? Radiated electric field from the fit antenna in the far field of the fit antenna, which is denoted by EF. F is for the fit antenna. I am trying to find out the radiated far field electric field of the fit antenna. It can be expressed like this: E naught F theta dash hat F phi dash hat exponential minus j beta r dash divided by r dash. That's the usual expression you have for the antenna in the far field. We usually use, let's say, horn antenna or open-ended waveguide. So let us find out what is dot product of n unit vector with the EF. So you have the n unit vector, you also have the expression for the EF. You do the dot product. So this has r dash and theta dash component, but this has theta dash and phi dash component. So when you do the dot product, only theta dash component will be existing, because theta dash and theta dash dot product is 1, all other terms will become 0. So you simply have sine theta dash by 2 E naught F theta dash exponential j beta r dash by r dash. And in the expression you have for the aperture electric field, you have something like 2n unit vector n dot EF. N dot EF, we have already find out what is n unit vector. Also we know it. N unit vector is this, 2 times of that, 2 times of n unit vector, and n dot EF, which we have just find out. This is the expression. And you also have minus EF for the expression on the aperture electric field. You have 2n n dot EF minus EF. So we want to find that. Then you do minus EF. Finally the expression turns out to be something like this: minus E naught exponential j beta r by r dash F theta dash r dash unit vector sine theta dash unit vector cos theta dash plus F phi dash unit vector. We have everything now. So if I want to find the aperture electric field, I need to take care of the movement from the 3D parabolic reflector to the 2D aperture plane, and that distance was 2f minus r dash. So the phase factor will be exponential minus j beta 2f r minus r dash. So we have the expression for the aperture electric field, theta and phi, theta dash and the r dash component. Theta dash, it has theta dash component, r dash component, theta dash component, and phi dash component. But the expression we have for the far field radiation pattern of a aperture antenna, we have done a generalized derivation, which was equation 24.1 and 24.2. It was for the x and y component of the aperture electric field. So we are interested in the x and y component of the aperture electric field. So this is for the theta dash, phi dash, and r dash components So I need to do a coordinate transformation from the spherical coordinate system for the source to the Cartesian coordinate system for the source. So what I want to find is Ea x dash, Ea y dash, Ea z dash in terms of Ea r dash, Ea theta dash, Ea phi dash. This is the coordinate transformation matrix. When you multiply it, Ea x dash will have expression like this, and the sine square theta plus cos square theta will become 1. So you can further simplify it. Ea x dash is equal to minus E naught exponential minus j beta 2f divided by r dash, f theta dash cos phi dash minus f phi dash sin phi dash. Similarly, you can also find out Ea y dash. So Ea y dash will be multiplication of this row with this column. Simplify it. What you have is Ea y dash is minus E naught exponential minus 2j beta 2f divided by r dash, f theta dash sin phi dash, f phi dash cos phi dash. You again replace this r dash by 2f by 1 plus cos theta dash. So the final expression for Eax would be E naught minus E naught exponential j2 beta 2f divided by 2f 1 plus cos theta dash, f theta dash cos phi dash minus f phi dash sin phi dash. Similarly, Eay is this. Let us look at Eaz dash. Eaz dash you can find out, it will turn out to be 0. So we have already established the x component and y component of the aperture electric field. What we are interesting now is, for the second step, is to find the 2D Fourier transform of the aperture fields. So you can find out the 2D Fourier transform. Let's say if I want to find Eax 2D Fourier transform of Eax, till there here means after doing the 2D Fourier transform, after the Fourier transform, you do the integration from 0 to d by 2 to 0 to 2 pi of Eax expression we have just derived. You multiply by exponential j beta dot r dash integrated over rho d rho d phi dash. So now in this case, since I have told you that aperture, what is the aperture? Aperture is at z is equal to 0. This is the aperture. So this aperture is at z is equal to 0. What is the value of theta dash for this aperture here? For this aperture here, theta dash will become pi by 2. At this point, theta dash will become pi by 2. So our actual r dash, now see here, this r dash means in the aperture plane, not in the parabolic reflector. Don't get confused. This r dash is for the aperture plane, and in the aperture plane theta dash is equal to pi by 2. In that case, r dash will become simply rho x hat cos phi dash plus y sin phi dash. I think I have another figure here. See, basically we are in this aperture plane. In this aperture plane, what is the value of theta dash? Theta dash will become pi by 2 here. This will become pi by 2 here. And in this plane, I want to find what is the r. Since theta dash is equal to pi by 2 and this distance here is rho, so in that case r dash will become rho x cos phi dash plus y sin phi dash. Theta dash dependence will go away, because cos of see, basically what do you have? R dash is rho sin theta dash cos phi dash sin theta dash sin phi dash plus cos theta dash. Sin of theta dash is 1, sin of theta dash is 1, cos of theta dash is 0. So r dash in the aperture plane will have rho x hat cos phi dash plus y sin phi dash. So this term here, we are actually doing the dot product of beta with r dash. So beta with r dash is beta. What is r dash? Beta will have 3 components: sin theta cos phi, sin theta sin phi plus cos theta. But when you do dot product, no, we are not interested in z component because our dash has only x and y component. So r dash has only x and y component. When you do the dot product, b dot r dash will only require this term and this term. So b beta rho sine theta cos phi dash sine theta sine phi dash. Again, you can take out beta rho sine theta common, then the remaining term here cos phi dash plus sine phi dash will become simply cos phi minus phi dash. So you can express this 2D Fourier transform in the more simplified manner here. Your integration, double integration going from 0 to d by 2, 0 to 2 pi eax dash. This exponential term you can express as exponential j beta rho sine theta cos phi minus phi dash rho d phi dash. We actually want to convert this integral over the fit angles. So this integral here is rho d phi dash. Rho 0 I want to convert it in terms of d theta dash, so that I do all integration over theta dash and phi dash instead of rho 0 here. What is rho 0 here? Rho 0, this is distance is rho here in the aperture plane. This is a small change in the rho which is 0 here. What is the relation of this rho 0 with that of the fit antenna here, fit angle of the fit antenna here? We need to find out that relation. No? What is d rho? D rho is equal to d omega here. This d omega and d rho will be same. No, this d rho and d omega would be same. What is this d omega here? This is this arc here is the arc of a circle, that is r dash theta dash. So d rho is r dash d theta dash. This arc here, this is angle d theta dash. So r dash theta dash d theta dash will give me d omega, and this d omega is equivalent to d rho from this diagram here. So this rho and d rho are the variables of this aperture, but we want to convert it in terms of the variables with respect to the fit antenna, which are called fit angles. So we replace d rho as r dash d theta dash. And what is r dash? R dash we have already derived it at the beginning of this lecture, first slide itself. R dash is f secant square theta dash by 2. So look at this diagram. What is this rho here? Rho is basically r dash sine theta dash. This rho and this distance is same. So that is basically r dash sine theta dash is this length here and is equal to rho here. So rho becomes r dash sine theta dash. What is r dash? R dash is so you have r dash sine theta dash. You can convert this sine theta dash as to sine theta dash by 2 cos theta dash by 2. So rho will become, what is this r dash here? F secant of square theta dash by 2. So this rho will become 2f sec square theta dash by 2 sine theta dash by 2 cos theta dash by 2. This you can cancel out, then rho will become 2f tan theta dash by 2. What is f? F is the distance between this fit point or focal point with the center of the parabolic reflector. Theta dash is this angle, this ray max with the z axis. Rho is this distance here in the aperture plane. So we can replace rho by 2f tan theta dash by 2. After we do that, d rho is r dash theta dash and rho is 2f tan theta dash by 2. So rho 0 will be 2f tan theta dash by 2 r dash d theta dash. So you can replace that in the previous expression for the 2D Fourier transform, and what you can see is that the final integration will be respect to d theta dash and d phi dash. So d phi dash and d theta dash, and d phi dash is going from 0 to 2 pi, d theta dash is going from 0 to theta m 0 to theta m dash, and phi dash is going from 0 to 2 pi. So you can do this 2D integration and find out what is the 2D Fourier transform of the X component of the aperture field. Similarly, you can also do it for Y component of the electric field. And for simple fit, you have electric field of a simple fit antenna. You can do this 2D Fourier transform. But let's say if you have a very complicated fit antenna, then you can even do numerical integration. So the second step is over. We have already established the first step. We have established the field and the aperture. Second step, we have already done the 2D Fourier transform of the aperture field. The third step is use equation 24.1 and 24.2 to find the far field radiated patterns of the reflector antenna. This is the relation you have 24.1 and 24.2. Here you have 2D Fourier transform of the magnetic field as well as electric field. So I want to simplify this for our particular case where we have a relation in the far field of the antenna. Is A is equal to 1 by eta naught Z cross EA. So Z cross EA will have EAX and EAY. You do the dot cross product, then finally ICAX can be replaced by 1 by eta naught EAX. ICAY can be replaced by 1 minus 1 by eta naught EAY. In the previous equation for 24.1 and 24.2, you replace ICAX in terms of EAX, ICAY in terms of EAY. Then the final expression you have is very compact one. Electric field in the far field of the reflector antenna theta and phi component is j beta exponential minus j beta r by 4 pi r 1 plus cos theta EAX tilde cos phi plus EAY tilde sin phi. Similarly, for the far field of the reflector antenna, phi component is similarly like this. You have the expression for EAX to the Fourier transform, EAY to the Fourier transform. You can find out the field. So we have got the fields for the reflector antenna, and the next thing we need to find is gain of the reflector antenna. So gain of the reflector antenna is the standard expression for the gain of the antenna. Efficiency of the aperture 4 pi by lambda square area of the aperture. Lambda is the operating wavelength. So now this aperture efficiency can be reduced into three terms. One is the epsilon r, another is the epsilon illumination efficiency, and epsilon activation efficiency. There are three terms here. Epsilon r is the radiation efficiency. That's a radiation efficiency you usually have for the antenna. We have other efficiency here which is called illumination efficiency, and it is equal to product of the two other efficiency. One is the taper efficiency, another is the spillover efficiency. So illumination efficiency is the product of aperture, taper efficiency, and spillover efficiency. We'll define all this term one by one later on. What is this epsilon A? Epsilon A is the achievement efficiency. It is dependent on another 5 efficiency here. First is epsilon RS. RS means random surface error efficiency. So when you manufacture this parabolic reflector antenna, you cannot have the ideal shape. No? There may be some change in the shape. Due to that, there will be some efficiency loss. That is called a random surface error efficiency. Second one is the cross polarization efficiency. The cross polarization efficiency is due to the fit antenna. No? So in the fit antenna, let's say you can have a X polarized wave or Y polarized wave, but usually all the antennas will have some cross polar component also. We are assuming that the reflector is in the far field of the fit antenna, and this fit antenna cannot have pure polarization. It will have some cross polar component also. Because of that, we'll have some loss in the efficiency. This is called cross polarization efficiency. Then we also have efficiency due to blockage. I have already told you about this blockage. Some of the rays which are reflected from the parabolic reflector will be blocked by the fit antenna or the support which will keep the fit antenna. or any kind of hardware you require for the field antenna will block the signals which are reflected from the reflecting parabolic reflector, would be blocked by the field antenna, which is usually kept at the focal point, at the focal point for the prime focus reflector antenna. So because of that blockage, there will be some efficiency loss. So this blockage efficiency loss would be due to some structures you have placed in front of the reflector, such as the field antenna, sub-reflector. If you have a dual reflector antenna, you will also have a sub-reflector, secondary reflector, or you need to support those reflectors, secondary reflector or field antenna. You need to support it. It cannot be kept on hanging. You need some metal rods to fix it so that it can be supported. Those kind of structure will also block the signals which have been reflected from the reflector antenna. So these are called aperture blockage efficiency. And you also have epsilon phi r. This is the reflector phase error efficiency. See, this reflector phase error efficiency may be due to reflector design shape variation. When you manufacture this reflector, or when you design this reflector, the shape may not be properly designed, or may not be properly manufactured. This is one case. Another is that the reflector, for the prime focus reflector, you put the reflector, you put the field antenna at the focal point of the parabolic reflector, but it may not be properly placed. It may be displaced from the focal point of the parabolic reflector. This is called defocus. Reflector is defocused. Because of that, you may have some reflector phase error efficiency. This reflector phase error efficiency may be due to the imperfect fit antenna phase center. Your antenna which is feeding the reflector is also another antenna that will also have some phase center, and that phase center may not be properly designed or fabricated, or phase center may not be properly used in the design. So in that case, there may be some phase error efficiency also. So the main efficiency we need to worry about the gain of reflector antenna is the illumination efficiency, and it is composed of two terms. One is the taper efficiency, and another is the spillover efficiency. You have come across the aperture taper efficiency. Due to the cosine taper efficiency, there is a loss in the gain of the reflector antenna, similar to that of the open-ended waveguide, or let's say horn antenna. Taper efficiency is very clear to you, but spillover efficiency is a new efficiency we'll be considering. So let's say look at this diagram here. This is the reflector here. This is the parabolic reflector. Signals which are gone from this field antenna are shown by these rays here, blue rays here. You also have some violet rays here. Any signal which has gone following this path here, shown by this violet rays here, it won't be able to hit the rim of this parabolic reflector, so it will be wasted. This is called spillover. So the pit pattern which goes beyond the rim of the reflector, that associated power will not be redirected by the reflector into the main beam. So because of that, gain will be reduced, and this is called spillover, and efficiency due to this is called spillover efficiency. And we'll calculate this spillover efficiency in the next slide. You also have another efficiency due to the taper, cosine taper, or any kind of taper of the aperture field. There will be another efficiency. This is called taper efficiency. When you multiply or combine this taper efficiency and spillover efficiency, what you have is called illumination efficiency, and it takes account of the pit pattern and reflector effects in a major extent. So these two efficiency are the most important efficiency for the reflector antennas, and we'll calculate this in the next slide. Let us assume that the radiation intensity of the field antenna is given to us. Once you have the radiation intensity, you can find out the fields in the far field of the fit antenna. So in this particular exercise, we'll assume that radiation intensity of the fit antenna is known to us. In that case, how do I find the taper efficiency? Taper efficiency can be simply found out, and you have the standard formula for the taper efficiency. You can derive it. This derivation, I don't have time for this. If you want, you can always derive this on your own. It's simple to derive it. You can start with this radiation intensity, find the electric field, and from the definition of the taper efficiency, you can find out what is the taper efficiency. And it has been, the final expression has been given here. Taper efficiency is 1 by pi cot square theta m dash by 2. What is theta m? Theta m is the maximum value of the theta dash. This is at the S of the rim of the parabolic reflector. Integration from 0 to 2 pi 0 to theta m dash, maximum value of theta dash, square root of u theta dash phi dash. Tan theta dash by 2 d theta dash d phi dash, square of that, divided by, in the denominator you do the integration over 0 to 2 pi 0 to theta m dash u theta dash phi dash sin theta dash theta d theta dash d phi dash. That's, you can easily derive it. We actually don't have time for the derivation now. So that's a taper efficiency. You can also find out, this should be spillover efficiency. See, basically, as I already told you, any rays which has gone from this part here, shown by this violet arrows here, which is outside the rim of the parabolic reflector, that is the loss of power. So now, any rays which has gone inside this portion here will get reflected back, and will be able to have proper radiation from those kind of rays. But those kind of rays which has gone beyond the rim of the parabolic reflector antennas are wasted. But this fit antenna, depending on what kind of antenna you use here, it may have rays gone towards this direction, or it may confine in this region here, and that would be understood from this radiation intensity here. Once you know the radiation intensity, you can find out how much signal has gone out of the rim of the parabolic reflector, how much has been confined in this rim of the parabolic reflector. So that ratio is basically given by this spillover efficiency. When you do integration, phi dash will be going from 0 to 2 pi, but here your theta dash will be going from 0 to theta m dash, u theta dash phi dash sin theta dash d theta dash d phi dash. This looks like the expression you have for the total radiated power, but then here this total radiated power will be confined only in this, within the rim of the parabolic reflector. That much power is the useful power for this parabolic reflector antenna. Anything which has gone beyond that, that's not used by this parabolic reflector antenna, and that's a waste of power. But this antenna is radiating fields in all directions. Let's say in that case, you will have fields which has gone beyond the rim of the parabolic reflector. So we need to find out how much the total radiated power from this antenna, which is a fit antenna. So you just do the integration of u theta dash phi dash sin theta dash d theta dash d phi dash 0 to 2 pi. Don't forget that this limit has changed now, 0 to pi. We have taken all possible values of the theta dash, 0 to pi. This will give me the total radiated power from this fit antenna, and this is the total radiated power which has been reflected by this parabolic reflector. So that ratio will give me the spillover efficiency. If I multiply this spillover efficiency and taper efficiency, I get the illumination efficiency. What you can observe is that this denominator here and this this denominator here and this numerator will cancel out. What we'll have is only this numerator and this denominator here. This is exactly what you have here. So this is the illumination efficiency. So in this class we have discussed about the parabolic reflector antennas, and we have found out the far field radiated patterns of the parabolic reflector antennas by following the 3 steps. Stabilize the field in the aperture. Then when you establish the field in the aperture, you use geometric optics, because parabolic reflector antennas are huge. in size, it diameter is greater than 100 times lambda, so you can use geometric optics, and we use geometric optics to find the aperture field of the parabolic reflector antenna, and from there we have found out the 2D Fourier transform of the aperture field and use that in equation 24.1 and 24.2 and find the far field radiated pattern of the parabolic reflector antenna. After that, we find out the gain of the parabolic reflector antenna, and such kind of big antennas usually have huge gain, and in the gain of the parabolic reflector antenna you have the usual stuff 4 pi by lambda square, then area of the aperture, then you also have radiation efficiency, then you have illumination efficiency. Illumination efficiency can be divided into two parts, one due to the taper efficiency, another due to the spillover efficiency. Spillover efficiency is the new efficiency we have considered here. You also have another efficiency which is called achievement efficiency. Achievement efficiency will have 5 terms. One is the first term is the surface roughness due to the change in the design of the parabolic reflector antenna. We have surface roughness efficiency, then we have cross polarization efficiency. Depending on the fit antenna has cross polar component or not, we can have cross polar efficiency, cross polarization efficiency. Then you have phase array efficiency from the fit antenna, phase array efficiency from the reflector antenna. Then you also have the one more is there, you also have the blockage efficiency. Some of the rays has been blocked by the hardware circuitry which actually hold the fit antenna, as well as the fit antenna itself, which is placed at the focal point for the prime focus reflector antenna. There will be blockage efficiency also. That's all for this class. Thanks for your attention.